All right, hello and welcome back, ALEKS students. So in this video, we're going to be talking about using the maximum work theorem with chemical work. I have already made an easier version of this topic. So if you're watching this video and you are need extra help, you need some sort of more fundamentals, go and watch that other video first. In this video, I'm going to sort of just pick up with some of that stuff that I've already talked about, the idea of transferring energy that's going on in these topics. Really sort of jump into this one that's a little bit more involved, a little bit more challenging. So, feel free to take a step back if you need to. So in essence, like I said in the other video, what we're talking about here is a transfer of energy. And so we've got two processes here where we're talking about the reduction of iron oxide to form pure iron. So here we've got this chemical reaction up here where we're forming an iron, solid. And then it says, is this reaction here, the production of pure iron is driven by the high temperature combustion of coke, a purified form of coal. So here we've got this carbon solid, that would be the coke, purified form of coal, reacting with oxygen, burning in oxygen to form CO2, right? So essentially what we're saying here is that we're going to generate energy in this reaction here. There's going to be an extra amount of energy that's, chemical work that's generated, energy that's released. And then this reaction up here is going to be absorbing that energy to drive that reaction forward. So again, we're transferring energy from one reaction to the other. That's what's going on here. That's a whole take-home message about chemical work. We're going to be generating energy, we're going to be absorbing that energy and driving a process forward. Okay, so what's really confusing about this problem in particular is how we're supposed to figure out what our delta G's for these two given reactions are. In previous other versions of this topic, we're given some of that information, but the way in which we're given the information for these two reactions is actually from these words right here. So it says, suppose at the temperature of a blast furnace, the Gibbs free energy of formation, delta G of formation of CO2 and iron oxide are minus 434 kilojoules per mole and minus 800 kilojoules per mole respectively. So what I've done up here is I've rewritten these words essentially into the chemical reactions that they are describing. So a delta G of formation, and so really we need to take a step back to delta G of formation. What that is it's a chemical reaction for the formation of CO2. So I'm going to be forming CO2, and it's going to be formed from its sort of elemental, components. So elemental carbon, elemental oxygen. So we know that's O2, right? And then that's going to be combining to form our 1 mole of CO2. And this is the delta G. This is the Gibbs free energy for this reaction. That's what this is telling us. Same thing here for iron oxide. I need to rewrite these words as, okay, well, what's the formation, reaction for iron oxide where I'm going to be forming 1 mole of iron oxide? Well, I need 2 moles of iron solid, right? Because I've got 2 as my subscript here. And then I need 3 moles of O3 or of oxygen. And so I'm going to need 3/2 of this O2 in order to get that O3, right? So if you're familiar with the Gibbs free energy and you're familiar with these formation reactions, you should be good at this, but this is essentially what this is saying. So then this reaction here has a Gibbs free energy of minus 800 kilojoules. Now we need to use this information to figure out what the information is for these given reactions, because this is really what we need to be able to do or sort of know about to do this problem. Now, I'm going to write delta G over here, and we need to use this information over here to figure out what the delta G's for both of these reactions are. Now, the bottom one, you'll notice, is the exact same as this, right? So the bottom one's pretty easy because we know that it's the same, essentially as that formation reaction. So the delta G for the bottom reaction is just minus 434 kilojoules. So in essence, what we're saying is that as we burn this carbon, we're going to be releasing some free energy. That free energy can be transferred into chemical work. That's going to be doing work on this top reaction. Now for this top reaction, we notice that there's some similarities, but they're not exactly the same. So we need to ask ourselves, if this is a known reaction with a known delta GF of minus 800, what do I need to do to this reaction in order to get to this reaction over here? Well, hopefully you can see that we need to flip it over, right? So we just need to flip the reaction over, and then we need to multiply it by 2. If I flip this reaction over, the sign on my delta G will flip as well. So if I flip the reaction over, then I'll get a delta G of positive 800 kilojoules. And then if I multiply by 2, if I look at my coefficients here, I need to multiply all of these by 2 in order to get to the coefficients that I see in this reaction over here. So I can see that my delta G for this reaction will be plus 1600 kilojoules. So for this reaction as written, the delta G for this reaction to drive that reaction forward is going to be positive 1600 kilojoules. And again, I got to this number by taking this known reaction, flipping it over, which will change the sign, and multiplying everything by 2, because it'll be twice the amount of energy that's required. So hopefully that makes sense. If it doesn't, feel free to comment below, and I'll try to specify that a little bit better. Okay, so now we can start working on the problem. It says calculate the minimum mass of coke, so the minimum mass of that carbon solid, right? So we need to specify that this is that carbon solid, needed to produce 110 tons of pure iron. So I'm going to start there, that 110 tons of pure iron. I know that that's what I'm going to need to form, 110 tons of iron solid. So I want to figure out how much energy is it going to take in order to form this 110 tons of iron, right? I know that in this top reaction, I'm going to be forming iron. I know how much energy it takes to do that. It takes 1600 kilojoules to form 4 moles of iron. Keep in mind, these coefficients are very, very relevant. So, I want to figure out how many moles are in 110 tons. So they tell me that 1 metric ton equals 1,000 kilograms. So I'm going to convert into kilograms first. So 1,000 kilograms is 1 ton. I want to convert this kilograms into grams. And I know that 1,000 grams is 1 kilogram. So just doing my dimensional analysis here, we can see that our units will cancel. And if I do this calculation, I'll be left in terms of grams. We could go ahead and take this one step further and convert from grams into moles, because I know that I want to convert into moles of iron ultimately. And then the molar mass of iron is 55.845 grams. So I can do this one big dimensional analysis problem, and you can do this stepwise as well, right? But I can do this all in one calculation to figure out how many moles of iron there are in 110 tons. And that ends up being equals 1.9697. I'm just going to carry my digits here till the very end, times 10 to the 6th moles of iron. So again, my first conversion here is basically saying they're asking me to produce 110 tons of pure iron. I know that this top reaction is sort of going to govern how much energy that's going to require to produce that iron. So therefore, I'm going to figure out how many moles. So just doing this conversion dimensional analysis will get me to my number of moles of iron. So then now the question becomes, how much energy is it going to take to generate this number of moles of iron? So I know that for every 1600 kilojoules of energy that I have available, I can produce 4 moles of iron. So I'm just going to do another essentially conversion factor where I say, okay, I know that it requires 1600 kilojoules for every 4 moles of iron. And again, I'm getting these numbers from this balanced chemical reaction. So, coefficients are very important. This calculation is then going to be equal to 7.879 times 10 to the 8th kilojoules. So sort of running out of energy over here, or running out of space. We've got plenty of energy. It's getting to be late in the day, so maybe I am losing energy. But this is the energy required. Energy required to form our 110 tons of iron, right? So this is the energy that I'm going to need to have available, essentially. So then the question becomes, where does this energy come from, right? So how do we generate this amount of energy? This is the energy we need to produce our 110 tons. Where does that energy come from? That energy comes from burning the coke. So then we're asked to figure out the minimum mass of coke, that carbon solid, that I'm going to need to generate this amount of energy. So this just becomes, again, basically a conversion factor, a dimensional analysis type problem, where I'm going to say 7.879 times 10 to the 8th kilojoules. And I'm going to use the information here to basically figure out if this every 1 mole produces 434 kilojoules, how many moles of carbon am I going to need? So I know that 1 mole of carbon, or coke, is going to generate 434 kilojoules of energy. Now, don't get caught up in the signs here, right? Because essentially what we're saying is that, this minus here is energy that's going to be released. So this might look confusing here, and you might sort of do this calculation and sort of say, well, now I have a negative number of moles. Really the signs, as long as you understand what it's representing essentially, then what I would just do is I would say, well, let's just convert this to a positive. We know that energy is being released. We're just doing a conversion factor. You could also convert both of these to negative values. Just, don't get too caught up in that. Basically all it's saying is what we're looking for is the number of moles that are required. So when we do this calculation, that's going to be 1.815 times 10 to the 6th moles of carbon or coke. And again, if you had left this as a negative and then you do this calculation and you get a negative number of moles, just try to understand what that represents or why you would get a negative value there. Really, I think to be totally proper and correct, we would say that this is the amount of energy that's required. So then we need to figure out how much energy would be released. So then we would put a negative sign here. Whenever we're talking about transfers of energy, from one perspective, it's going to be negative. From the other perspective, it's going to be positive. So, again, don't get too caught up on that. But in any case, this is the number of moles. And now all we need to do is essentially convert from moles into kilograms. We know that this is the amount of that coke that we need in order to produce that amount of energy, which will then be absorbed by this other process used to do that chemical work to form our pure iron. So the last step here, 1.815 times 10 to the 6th moles of carbon. So I'm just going to convert that into grams first. 12.01 grams of carbon for every 1 mole. And then we can convert that. It's asking for the answer in kilograms. So we can go ahead and convert that to kilograms right away. 1 kilogram over 1,000 grams equals 2.18 times 10 to the 4th kilograms. And then we're asked to convert to 2 sig figs. So this would be 2.2 times 10 to the 4th kilograms of that carbon, of that coke. That's going to be the mass that you need in order to generate this amount of energy, right? And then that amount of energy is going to be what's required to convert your iron oxide into iron. So again, take-home message: transfer of energy. We're generating the energy in one sense and we're absorbing that energy in the other sense. That's sort of the way that this all goes. And then we just need to basically do 2 separate problems where the energy that's being transferred, right, that's sort of the common value between the 2 different processes. So in this case, this is the amount of energy that's required, from this amount of carbon. When I burn this amount of carbon, sort of working backwards, if I burn this amount of carbon, then that's going to be this number of moles. And based off of this, reaction up here, that's going to generate this amount of energy. That amount of energy is then being applied to converting that iron oxide into iron. And this amount of energy would be able to convert 110 tons of iron, which sort of brings us all the way back. So again, pretty involved here. I think that the really confusing aspect is using, figuring out what these values are sort of telling you, how to tie that back into what your chemical reaction delta G's are, and then, obviously putting it all together. So let me know if that helps. Let me know if you've got other questions about this, but thanks so much and have a good one.